No.
The broadcast is now starting. All attendees are in listen-only mode.
Good morning and good afternoon, depending on your location. Welcome everyone to the SOLIDWORKS Simulation, What's New in 2017 webinar. My name is Dave Leahy with Desai Solutions over in Michigan, and Sean Bentley, our application engineer, is here with me today to go through some of the new things that are in SOLIDWORKS Simulation and SOLIDWORKS Flow Simulation. So we've got quite a few people. I think we had almost around 75 people sign up for this, customers. So we're going to give you a few minutes to get as many of you as we can logged in here, and we'll get started here in about a minute. Thank you. So maybe while we're waiting for others to join, we can start here with a poll question. Part of what we want to understand is, since we have a large audience, we want to get a better sense of how what your experience level is with SOLIDWORKS Simulation. So if you could go ahead and answer this question as to your experience level with SOLIDWORKS Simulation. We'll get started as soon as we get some responses to this. All right, looks like we've got everybody there. It currently looks like we have quite a mix. Mostly, we have about 25% that are new to SOLIDWORKS Simulation, and 20% that use it for linear, 23% for nonlinear. So we're going to talk a little bit about some of the nonlinear pieces. So it looks like a wide variety of customers, pretty evenly split all the way across.
Yeah, it does look pretty.
All right.
Pretty even.
Okay, so I'm going to close out on that and turn it over here to Sean Bentley, who can kind of go through some of the new things in SOLIDWORKS 2017. We appreciate your time today. Thank you.
All right, so we'll go ahead and get started with some of the content for today. So on the agenda, there's a lot of stuff that's new inside of SOLIDWORKS Simulation and also inside of Flow Simulation. You can refer to the What's New PDF for more details. I've picked out a few selected items, ones that I can kind of demonstrate a few things about, but a lot of the other items that I didn't pick, you can almost just read about them and get the idea of what they're doing with a lot of the, but these are the ones that were a little trickier, I think, to get a rough idea on what they're doing. So from the structural simulation side, we're going to look at detecting stress hotspots, offloaded simulation, also some of the additional contact added to the nonlinear arc length control option, self-dismiss messages, and macro recording. Then later on we'll talk a little bit about what we're going to do in Flow. So let's take a look at the structural side, starting with the detecting stress hotspots, the new detecting stress hotspots tool. So this is a tool that will track down singularities in your model. And it does a pretty good job of it. What I'd like to do is maybe show this model that I have on the screen. It's a very typical sharp corner kind of an example, and let me explain what this tool is going to do. So here I've got a simple study set up where I've fixed one end of it, applied a vertical load to the other. So theoretically, we're going to have a stress singularity in this sharp corner here. Basically, the stresses will be projected to be infinite, but we talk a little bit more about stress singularities in our training class if you're interested. But here, if I run the study, it looks like there's a stress riser there. Looks like the stress just grows, and I'd have to do mesh refinement to see the stress grow more and more and more without bound. So what this stress hotspot tool is intended to do is it'll factor out the stresses from some of these infinite regions, because the stress there can't be trusted anyway, because I didn't really model that region very accurately without putting a fillet on there. So to run this tool, I'll just launch this new stress Hot Spot Diagnostics is what they call it here in the results folder. You can set a sensitivity factor, so setting the sensitivity very high will filter out more than setting the sensitivity low. It's just a simple slider that controls how sensitive it's going to be. And then if I go ahead and run the tool though, when I run it, it sort of explains a little bit of what a stress singularity is. It's showing that the stresses grow without bound. I'm just going to click OK to it, and then here you can see the it factors out, kind of grades it out. You see on the far right here, it grades out the maximum stress region and readjusts that maximum to be representative of the more accurate regions. You see it also grades out the region near the fixture. Perfectly rigid fixtures are also singularities, believe it or not. Now, if I set up a scenario where it's non-singular, if I put a small fillet on here, okay, little fillet, and also instead of using a perfectly rigid fixture, use something called an elastic support, which allows the material to stretch a little bit, and I run that same singularity tool, that stress hotspot tool. Use a very high sensitivity. It reports correctly that it wasn't able to detect any singularities or what it calls hotspots. Okay. Now, so the tool is pretty robust. You can, with some trickery, you can get it to read false positives and false negatives, but these are very particular scenarios. Like here, I was able to get it to read out a false positive. If I have this fillet here, if I just mesh right over top of the fillet by using the tolerance, so you see if I somehow get the mesher to go right over it, then it will, the stress hotspot tool will report that as a singularity. So it does give me a sort of a false positive there, but I think it does a pretty good job even in this scenario of identifying the correct singularity areas or not. So I'd like to move back then here. So what I just showed there was, again, that stress hotspot tool allows you to filter out the inaccurate stress regions, the ones that have singularities, from your result plots. So you'll be able to report on the more accurate regions. So it helps to reduce some errors. So next what I'd like to do is take a look at our another new tool, Offloaded Simulation. That's what we call it. What this tool does is it allows you to run simulation virtually over a network. So here I've set up two virtual machines to sort of demonstrate this idea. So on the right here I have what I'm going to call the host machine. This is the machine where I set up a simulation study, I apply the fixture load and all that. And then when I click run, it's going to transfer that data over into this other machine. This is a completely separate workstation that I've kind of remoted into. So it'll transfer those files over into this folder, and then this worker agent will do the solving of the simulation for me. Once it's done solving, it's going to transfer the results back over to the other workstation. So just to demonstrate this, so here I just did a recording here. I'm going to manage the network just to show you the couple of solvers that are available to me. So here I have the solver I'm going to send it over to. I've also got a bigger one on there as well that I can use, but I'll just make use of this solver machine that you see on the left. So on the left machine here, I want to activate the SOLIDWORKS Simulation worker agent. So just a simple button click, and then that'll turn that feature on. So now it's ready, it's waiting for a simulation. Now you don't have to always just do that activation that way. You can set up a batch file if you put this little script in there, and this will activate every time. You can set it up to where it activates every time you boot up the machine, so the simulation worker agent's just always active on that machine. You don't even need to leave that window open that I left open, but I just left it open so you can kind of see the behavior here. Now if I go ahead and run the study on the host machine, you'll see the data transfers over, and you see it in this folder here. I'm waving my cursor on it. See the data transfers over this folder, and then it proceeds to actually run that study. So this machine has a little bit more processing power than the original machine. I do have another machine that has quite a bit more processing power that I could use for future studies as well. Now, if it does have to transfer a lot of data, if your result files are really big, the this worker agent tool can actually take longer to run the study. So the worker agent's probably best for studies that have relatively small result files but have long run times. Things that have a lot of no penetration contact are going to be good examples there. So it looks like it's already done running, and then just wanted to show, if I go back to manage network, I did have another machine available that had more RAM, more cores, faster processor speed. This one I actually have is over a network connection as well. So more details can be found in the help file for how to get this sort of environment set up. They kind of walk you through step by step. So what I showed you there was the offload simulation tool, which allows you to run simulations over the network. So that frees up your personal machine, so you can continue to do other things without tying up all your computer resources. So next, what I'd like to do is take a look at this new no penetration contact that they've added. Well, the no penetration contact itself isn't new, but the fact that it's included now in the nonlinear arc length control method is new. So a little bit more on this subject. It's a bit abstract, so I'll break it up a little bit. So when we're talking about the nonlinear arc length control method, most of the time where that method applies is to buckling problems. It does apply to a few other problems, but probably the simplest one to apply it to is going to be buckling problems. So we have a couple different tools to analyze buckling. You can use our linear buckling tool, which we see on the left here, which has a certain amount of capability, without getting too much into the weeds and details of it. Then we have nonlinear static, which this is the tool that uses the arc length control method that I'm going to talk about in a moment here. Has a little bit more capability as far as buckling goes. And then there's also nonlinear dynamic, which has yet even more potential capability, but with the added expense of perhaps longer run times, additional assumptions, and additional setup required. Okay. So a lot of buckling problems can be run sort of in the middle of the road here. It's sort of like a compromise between accuracy and speed. And what we've done with this enhancement is we've improved the capability of this nonlinear static type. We've added a little bit extra capability by giving it the no penetration contact. So what I'd like to demonstrate then is a particular example. If I run something in buckling, the kind of results you might get, then also show a little bit of nonlinear dynamic and the results you might get, and compare that to how we might now use the arc length control method with no penetration contact. So if I were to run a linear buckling scenario on, let's say, just a simple beam, or in this case a meter stick, just to make it a little bit more intuitive, less abstract, we might expect to see one of two buckling shapes. One buckling shape that we might see, depending on how thick the meter stick is and exactly how you're pushing down on it, if you're using the palm of your hand, which is really soft, or if you're using something rigid, which might actually exert a little bit of a moment, you might get two very different buckling patterns. One pattern might require about 100 newtons, about 93 newtons to buckle it. The other one, almost a quarter of that. Okay, so very different results that you get out of these two buckling modes. Okay, so which one's the right one? Well, if I run a nonlinear dynamics study, I can get a little bit more insight into which one might be the right one. So here's what the results of a nonlinear dynamics study. This study took a little while to process and set up, so it's a much higher level of detail than maybe what I need to go into. But in the nonlinear dynamics study, if I just play this animation, you can see it actually buckles. If I assume that there's a rigid connection up here, it actually buckles using both modes. It buckles with the that large mode, that first mode I showed you in that previous slide initially, and then it snaps to the second mode. Okay, and it looks like it's probably due to the fact that I assume that this test fixture is very rigid, and it exerts a little bit of a moment on that to keep it from freely rotating like a hinge. Okay, now if I use my soft hand there, that might be quite a bit different. So virtually in the nonlinear dynamic, it basically says that it's like both results are kind of right, but it looks like as long as you have the stiff geometry up here, it looks like the buckling load factor is around that 93 level, the one that I saw in that earlier slide. So now, like I was saying, with nonlinear dynamic, you'll have to make some assumptions, maybe scale this damping factor up and down, exactly what to key in for the damping factor. You'd have to play with it, and there's a few other things. It can be a little more complicated to set up compared to the nonlinear static. Okay, so what I'd like to demonstrate briefly is an idea of how to use this new no penetration inside of a arc length control nonlinear static analysis. So opening up this meter stick here, I've got a couple of nonlinear studies set up. One, this study I've created just has simple loads applied to it. One interesting thing to point out, I've applied a tiny side load to sort of instigate it to buckle one way or the other. So it's sort of like I'm telling it choose a direction, or I'm going to pick a direction for you if you can't choose it. So just give it a little bit of a push one way or the other. And then another interesting thing to point out is I modeled the my hand up here, so to speak. I just used a material that has a very low elastic modulus to sort of soften the structure to see what kind of buckling modes I get with a softer structure on the top. So the net result of these, some of these characteristics might look like this in an animation form here. Let me rotate to a little better angle here. All right, so you can see the deformation of my hand around that, and you can see that it looks like it behaves more like a hinge up here. It doesn't do that other first mode bending pattern. So, and then down here where it's rigid, you can kind of see that bending pattern though. Okay, so if I were to soften that structure up down here, I might get some different results as well. Okay, and actually instead of the load factors I was seeing before, I was seeing a load factor around 93 in some of the earlier slides. That was on the high end. Here I get a load factor quite a bit less, somewhere in the order of about 50. Okay, so 93 when it buckles in the most rigid form, 23 when it buckles in the most flexible form, and really it might be somewhere in between depending on exactly how these end conditions are constrained. So with this new no penetration contact, it gives you a lot more flexibility with how you constrain things. So that gives you it gives you potential to be more accurate and quicker than having to run it on the near dynamic study. All right, so next, I'd like to move on to this next one. This one's a pretty quick one, I think, to illustrate. A new tool, or basically a new option that automatically dismisses messages. So to talk a little bit about this, let's say I wanted to run a drop test study on in this case I got like a cup of water or something here, or a cup of coffee. And so I want to try a drop test on it. And so I set up the study and I hit run, and then I walk away. You know, I go and grab a cup of coffee or go to a meeting, etc. And then so it's running the study, and then when I finally come back, 2 hours later, then I see this on my screen. Okay, so it looks like it's not done running yet apparently, but why not? Oh, it's because this dialog message popped up. Okay, and if I had been standing there watching it, the dialog message popped up maybe about 20 to 30 seconds into the run, and it's just been sitting there waiting for me to respond to it. Okay, so had it just automatically dismissed the message, it would have been done ages ago. I mean, it says it would have taken an hour and 20, and I've already waited 2 hours, and it's still not done because of this message. So what I'd like to do is just show you where this option is at, so you can turn this on. Because from my testing, it looks like it's factory default. This auto dismiss messages option I'm going to show you is turned off. So you may want to jot this down, or they do also have in the what's new document. So if you don't want these messages to pop up and basically stall your study while you're out at a meeting or at home sleeping, you can go to your simulation options and then turn this guy on here. It says automatically timed out decision solver messages, and I'll have this timeout after, like, say 10 seconds. So now when I run that study, okay. So when I run the study, when the message comes up in the title bar, it'll say it's going to dismiss it in 10, 9, 8. It'll start doing a countdown, and it'll also highlight to me which option it's going to pick if I don't pick it myself. So here it's doing the countdown in the top, saying, hey, it's going to take this much time. It's going to say, would you like to change the solution time and rerun? It's going to say no, and it's just going to run it. Okay. So later on, if I let it go ahead and run, so now it's continuing to run. If I let it run to completion, I will get a message later on that says it automatically picked no to that message, so it'll keep a log of what it did. Now, of course, I'm not going to let this run to completion, so let me kill that. All right, so now moving back to the slide there. So I did end up letting it run to completion just so you can see kind of the behavior of it. So cup landing on the ground. All right, but anyway, the next thing that I want to talk about is going to be a little bit on macro recording. So to illustrate this, let me go to that same model for a moment. So the new macro recording feature. So I set up. I have a little toolbar up here. Okay, I just turned it on, and you're just go to your customize and turn on toolbars, and then you can use this to record simulation macros now. So that's what's new. Previously you could record SOLIDWORKS macros. So this is like if you want to automate something, if there's a very repetitive task. One of the things that I find that's good to automate is a lot of times I'll be post-processing some results. I'll need to export a particular graph into Excel or something and then do some work on it in Excel. I'll create Excel macros to speed up the work in Excel, but to speed up the work in the SOLIDWORKS end of things, it'd be nice to be able to create a simulation macro on that end. So all I need to do is run the macro and it automatically exports to Excel some of that data. Now in this case though, I'm just going to show you just the simple recording. If I just set up a fixture and a load, and then show you how you can go in and start tweaking it. So if I go ahead and record, it's recording now, and I can set up a fixture maybe on the bottom face, set up a force maybe on, just pick a top face here, for example. I'm going to key in kind of a funny, like 1, 2, 3 or something. That way I'll be able to identify it in the macro in a moment. And then that's it. Let me go ahead and hit stop and save that macro. So now if I go and edit that macro, you can make my favorite thing about recording macros is that it lays out a lot of the groundwork for you. Okay, these are steps that I don't want to have to memorize, and you can always copy and paste from existing macros if you already have one. But then you can also come down here and make changes to the macro and tell it, okay, it's still 123 pounds, or 123 newtons, apply 1,000 newtons, that kind of thing, and then save that macro. So then the next time I run it, what was it, next time I run it, it'll apply that fixture and that other load. Try one more. But anyway, so the rough idea is then you can go in, you can make changes to it, and then just rerun it with those changes. Don't want to get too in the weeds. Now so when you edit it though, you probably want to edit out a lot of the extra lines of code. There's a lot of rotation, like because I did some rotating. So you'd probably edit a lot of that excess stuff. You don't need it to rotate every time you run the macro. So, okay. So back to here. Now, basically what I showed there though with the macro tool, you can use these macros to record common simulation tasks. Typically, you'll need to go in and edit them, clean them up a little bit, maybe even add to them. But it lays out a lot of that foundational work for you. Again, frequently my use for macros is for post-processing data. That's probably where I most commonly use it. When I run a study, export to Excel, run another study, export to Excel. That repeated exporting is one thing that is very macro handy. All right, so then what I'd like to do next, maybe move over into flow simulation and take a look at. I think this is probably my favorite. Oh, before I do, yep. What's up?
It's Dave. Real quick. Yeah, I just noticed we're starting to get a few questions. We'll answer those at the end. So just want to let people know if you do have questions, go ahead and put them in the question area, and we'll answer all the questions in the end. Thanks.
Okay, excellent. Yep, yeah, I just noticed that myself there. I'll have to. All right, so we'll have a section for questions towards the end. All right, so then next what I'd like to do is move into flow simulation for a moment here. This is probably my favorite enhancement this year as far as all the simulation tools goes, this MultiParameter Optimization. So to get into this here, so the rough abstract idea is that with pretty much any kind of
Dave, do you hear a buzzing sound, or is that just me?
I don't hear anything now.
Oh, okay, let me just do a little quick thing. There we go. All right, that was just my headset. All right, so then with the multi-parameter optimization is we're going to be inputting some parameters, in this case some model dimensions, and it'll be changing those parameters, and it'll run the study again and again and again, and it'll construct response surfaces. Okay, so it'll give us an idea what how the outputs respond to those different inputs. So it'll actually generate response surfaces, and then we can put constraints on those surfaces and try to minimize something or maximize something to try to optimize it. In this case, to make it a little less abstract, we're going to optimize this heat sink. Here I've got LEDs. I'm going to generate 100 watts total, and I want to play with the fin design and try to, my goal here is to minimize the mass of this thing, because maybe I need to produce thousands of these things, so try to save a little bit of cost, minimize the mass of it. And and my constraint is to make sure the temperature stays below, say, 85 degrees C. Okay, I'm not allowed to go above that temperature. So some of the variables I'll be playing with in a moment is just going to be the number of fins. Okay, so see, like I think 20 fins here versus 60. The thickness of the fins be another variable. So it's adding a lot of extra mass, but it is adding a lot of extra bulk heat that will be allowed to transfer to the fins. So I'm not sure if this will be better than that or not. So we're going to experiment with that, and then also the fin depth. Okay, so you can do. I don't think there's a hard limit on the number of parameters that you can do, but the more parameters you do, the more experiments you'll have to tell it to run to get an accurate response surface. Okay, so in this case, I'm just going to use 3 parameters, just those 3 fin parameters. So take a look at that. All right, so here I've set up a flow study on on this side of the domain. I have like room temperature air. On the opposite side of the domain, it's warmer air. It's like 90 to 100 Fahrenheit on this side because it's not as free cooled. And each of these LEDs is going to, or rather, the total wattage from these LEDs is going to be 100 watts. So now what's very important that you set up in your flow study, in your base flow study, is some goals. Okay, I've set up a max temperature goal to monitor the maximum temperature on that solid body there. And I've also set up a mass goal to monitor the mass of that solid body, okay? Because these are going to be the things that I'm going to use as constraints and as optimization goals. You need to make sure you set up these sensors beforehand before you jump into the optimization tool. So now with that in mind, I don't even need to run this study. Probably a good idea to run it just to see what kind of result you get, but I can move right into the what we call the parametric study tool. Let's create a new one. And this little drop-down, design of experiments. This is the new feature. Okay, we already have these 2 tools in 2016 and prior, but this is the new 2017 tool. This design of experiments and optimization tool. So with this design of experiments, I'll add a couple of dimensions. In this case, I'm looking for the pattern instance count, which is currently set to 60, and I'll click on it. So that way I'll be able to add it to this list. And then I'll vary that, tell it to go from 20 to 60, 20 the minimum, 60 the maximum. So then I would go ahead and add the other couple of dimensions. So I've already got that set up here in a moment, so I'll just show that in a second. But then once I set up all those dimensions, then I'd move over to my output parameters and tell it which goals that I'm interested in monitoring. So I'm going to add the couple of goals I created, the maximum temperature and the mass. Okay. So once I've set all that, once I've set all that up, then I'll move over to the scenario tab next. Now, since I skipped the other input variables, let me cancel this study, and I'll go to one where I've already keyed in the other 2 variables, and I'll be varying the thickness and the depth of those fins as well. So I've just added those. So my outputs, I've already got the sensors on there. So I'm going to move over to this 3rd tab, and here you can tell it how many experiments that you want to run. The more experiments you run, the more refined response surface that you'll get. Okay, you run very few scenarios, and it might not be able to optimize it too robustly. But the more experiments you run, the cleaner surface it'll be able to generate. Okay, so in this case, since I have 3 variables, I think maybe 25 is a good number to try. So I'll do 25 experiments, and then here's what it generates as soon as I just click that one little button. Okay. So it's going to vary those dimensions. It's using like a space filling algorithm to fill an n-dimensional space, like hypercube. So it's actually kind of really interesting how it fills out that space with these points, so it can try to figure out how these points relate to the temperature in the solid, so it can do the proper optimization on it. So now it does take a while to run, so I'm not going to hit run on this one. I've already got a completed version of it here. So here's a version where I already hit run. Okay. So now here you can see the results down here, the different temperatures and masses for each one of those runs. And just kind of scrolling through the results, maybe pick out one in particular, like this one here. I see the temperature is pretty high, the mass is kind of low. So this one might not satisfy a constraint, but it's certainly in the direction of minimizing the mass. So it seems to be in the trend of reducing the number of fins. This only has 20 fins, so it gets a little too hot though with only 20 fins. So you definitely see a relationship between the fin number, how many fins there are, and how hot it gets. When you look at this one right next to it, has way more fins, like 48. It gets to a much lower temperature, but is more massive. Okay, so again, it's figuring out those relationships, constructs response surfaces in the background. Okay, and now that it has that data to work off of, now I can find optimum. Think of this find optimum tool as like a tool you can use to explore the surfaces that it found in the background. So in this case, I'm going to try to minimize the mass. So I'm setting up this objective function to minimize, not temperature. So I'm going to zero that out. I'm going to minimize the mass. Now I'm going to add well, let me just see what that design point looks like. If I just go ahead and hit add optimal design point, it creates this optimal point over here. So here it calculated the minimum mass to be 2.09, which I think it's less than any mass that it actually ran in these experiments. So it's extrapolating from those response surfaces. Now that'll correspond with a temperature that's pretty hot though. So let me add a constraint to this. I want the constraint to make sure that the temperature, so this guy here, I'm going to put a 1 next to it. I want to make sure the temperature is less than 85 Celsius. Now with temperatures though, you have to be careful. It doesn't actually use the document units I'm set to degrees Celsius. It actually will use Kelvin. So I need to add to that 273. So that gives me a number 358.15, I guess technically, but all right. So then that'll make sure the temperature stays less than 358. So if I go ahead and add that, add that optimal point, adds that to the list over here. So there's that temperature. It looks like 80, well, close to 85, or there's that 0.15. I should have keyed it over there, but it's close to 85 degrees Celsius, and there's my minimum mass given that constraint. Okay. So how accurate is that prediction? This is just a prediction. It didn't actually pick any of these points. It's guessing that the results will look like this if I were to actually run a study with these dimensions. So how close did it get, I wonder? Well, I went ahead and ran the study. So just if you need, maybe jot down that number 2.46, and that's about 85, so 2.46. If I go ahead and run that study, here's the result I got. It's basically the same. No, 2.4. I wish I would have wrote down another decimal place. So I think it was 2.460 or something. Instead it says 2.467. And then the temperature was 84.85. Now it's 84.83. So it was really darn close. I think whatever response surfaces it's constructing in the background are giving me pretty good predictions. And so that can make me a little bit more confident that it did find a good optimum there. Okay. So again, very neat tool. There also looks like they're going to add the ability to view these response surfaces in maybe a later service pack potentially. At least they have the button integrated here, but it just doesn't work yet. So, but we'll see that maybe we'll see that pop up in a later service pack. So, all right. So what did we just do there? We took a look at the MultiParameter Optimization tool, and we used it to try to shave off some mass on one of our components, really to reduce the weight and make it cheaper to manufacture these things. So next what I'd like to do, take a look at the Transient Explorer, another new thing to flow simulation, specifically for transient analyses. Okay, so I'll look at this tool in the context of this drag problem. It's actually one taken from our training class. If you've been to it, it's like lesson 4 in our training class. But this is we're going to run this as a transient problem because we have some turbulence that causes the flow to oscillate up and down. So, and I want to try to calculate what's the frequency of that oscillation. Okay. So we'll use the Transient Explorer to maybe help a little bit with that and just to help us visualize the progression of that oscillation a little bit better. All right, so let me show the Transient Explorer and then where you can go to maybe enable it on your own machine here. So this is the new tool that they've added into Flow Simulation 2017. This little play bar here, which I had to activate the Transient Explorer to get to and run a transient analysis. So if I just play back the result here, so animate in time the development of that flow field. Okay. In previous versions, you have to kind of set this animation up a little bit more manually, and it can take up a lot of hard disk space without the Transient Explorer. So in previous versions, you'd have to tell it to save pressure, velocity, basically all turbulence parameters, all the results basically. Now what they've improved here is, again, first they've added this play bar, and another thing is if I go into the calculation control options, instead of having it save full results, which is this is the way you do it in 2016 and prior, we have this option down here to select particular parameters that we're interested in and use the Transient Explorer with those parameters. For example, here I can go in this list and tell it I really only care about animating velocities on a transient scale, so that's the only one I'm going to pick. So this makes the results file substantially smaller, okay, and much faster to actually load and animate and that kind of thing, because it has to load a much smaller amount of data. Okay. Now it does have to be, again, it has to be set up as a transient analysis, otherwise you won't see this Transient Explorer in here. Now another thing they've added, a little bonus here, is they've added like a goal plot widget, they've called it. Okay. So I've always wanted to be able to just right-click and hit Show on the goal plot. Now you can do that, and it shows the plot right in the graphics area here. And even with the Transient Explorer, if I go ahead and hit play, you can see it kind of follows that widget. Okay, you can kind of see in time what the X direction force looks like as we're moving through time. Okay. Now, just like we might do in the training, we can then take this graphic and try to convert it into a little bit of a frequency to figure out what's the natural frequency of what's the frequency of the oscillations. Okay. All right, so what we look at there, with the Transient Explorer, it's a tool that will expedite results post-processing, because it's not saving full results, it's only saving a subset of the full results, the ones that you care about. And also with the little play button down there, in prior versions you'd have to go through a whole wizard and try to set up an animation, and there's a lot of quite a bit of post-processing work. So they just sped that up a bit. They've reduced a lot of the button clicks just to show a transient animation. Okay, so they made it a little bit smoother, more efficient. Also, we looked at the goal plot widget, which allows you just to show the goal plot directly on the screen without having to export that to Excel or to a separate sheet. It'll always be there. And if you rerun the study, the goal plot widget will update as well. So just cleaner interface tools. All right, so then the how are we doing on time here? Oh, just about right. The last thing I want to show is using conditions from low-level components. So what you'll see in the What's New document is what they call it. Now, the idea here is if you have if you have an assembly or multi-body part, or if you have an assembly or multi-body part and you have a lot of repeat components, what we can do is we can set up sort of like a submodel simulation on one of the components, one of those repeat components, and then take those properties and then assign them to all the other repeats. Okay, so here's how that looks. So here I have my assembly, and I've got a lot of these little capacitors. You see, I got like 20 of them in here. If I just hover my cursor up and down, you can kind of tell where they're all distributed, quite a few. Okay, so what I'm going to do is I want to set up a flow analysis on this assembly. And to help speed that up, I'm going to open up one of these components, one of those capacitors that I want to set up some different conditions on, and I'll create a flow study inside of that component. So here I've already created a couple flow studies, and maybe I can make a copy of one of these and call it heat 2 watts. Okay. So here I've got a 2 watt heat source. So I'm going to just bump this up to 2 watts. Okay. And then this other heat source study, maybe I'll rename that to 1 watt, so it'll really stand out a bit better. Okay. So in the 1 watt heat study, this thing's generating 1 watt. It's also got radiative surfaces on it, so that tells it I've specified emissivity on these faces and also contact resistance, whatever component it's touching, it'll have a contact resistance on there. And I'm not even going to run this study. Okay, I'm just setting up these boundary conditions on it, and I've done the same kind of thing with this heat 2 watt and also with this 2 resistor one. I've just done something completely different with a 2 resistor component. But I can use these studies inside of that parent study now. If I just go ahead and save this. And now in this parent study, this is the new feature here, this from components option. This is brand new, it's 2017. This allows me to pull in the information from those studies. Okay, so here I see the capacitors all pop up because they're the only component in this assembly that I actually I bothered to set up a flow study on. Okay, and if I go over here and select project, you see here's the names of those studies I just keyed in. There's that 1 watt there, and maybe I'll grab the 2 watt there, and maybe another 1 watt, and another 1 watt, etc. Okay, maybe even grab a 2 resistor there. All right, so I can go through and tell it which projects to assign. Now, unfortunately, I haven't found a way to do a group selection yet, but you know, maybe that's something that's coming. But for now, you can just use little shortcuts here, like if I type in the letter H, you know, it'll automatically track through the list and do the assignment. So it's pretty quick. But once I've done all that, I'll go ahead and add to insert those features into the project. You see it adding all those features from those components. So now if I kind of expand this out, you see the 1 watt version has silicon applied to it, has the 1 watt heat source and the radiative surface and the contact resistance. Everything I put in that little sub-modeled study is already included. Okay, if I go to the 2 resistor version of it, there's the 2 resistor component that I put on that one. Okay. So what we just take a look at there, with the new from components option, you can import basically a lot of setup conditions from the components, from the component files. If you set up just a sub-modeled study in there, again, you don't even have to run the study, just set up conditions. Then you can import those conditions to really automate a lot of potentially repetitive things that you might do. Now, if you have like a fan, you can even import fan conditions. So you could set up you could open up one of your fans, set up fan conditions on it, and then when you get to the parent study, then you just import that study every time you need to use that fan. So just anything that it helps automate those potentially repetitive tasks. All right, so with that brings us to the end of our list here, but be sure to check out the What's New document for a little bit more details on some of these existing ones, and hopefully I made it a little bit clearer than just what the What's New posts in there. So maybe now we'll address any questions that we saw in the...
Yeah, Sean, if you want to kind of go through the questions. I think that the first question is from David, and
yep.
He's got a question on whether you need 2 licenses to run the remote.
Yeah, the answer to that is no. You do need a license of Simulation Premium currently, 1 license of Sim Premium. But then the way it works is that you have you install like the full SOLIDWORKS and Sim Premium on machine A, and then on machine B you just install the worker agent. You don't install SOLIDWORKS, you don't install simulation, just the worker agent gets installed on machine B, and then that machine becomes sort of a slave to machine A. When machine A you hit run, it'll process it on machine B. Okay. The next one was, does macro recording also work for flow simulations? That's a good question. I might have to get back with you on that one. I think the answer is no. I think they just added it for the structural side of things, but I haven't honestly tested it with flow, so I don't think that's implemented quite yet. Okay, but I can double check.
Than a SOLIDWORKS feature. Okay.
Yep, I think it's a SOLIDWORKS simulation feature, but I'd have to double check. All right, and then another question is MultiParameter Optimization related, looks like. Can one interrogate an optimal point prediction, or must they take those numbers and run a new simulation and take? Okay, I kind of answer that question. What you have to do is maybe I can just show it. I didn't answer it maybe directly, but I still have it open. All right, so when you run it, let me go to this one here. All right, so the way it works is that you know, when I add one of these optimal points, let's use the minimum mass one as an example. Okay, it makes that prediction, and then in order to know how accurate that prediction was, if you just hit the run button here, it'll just run any studies that are out of date, which right now it's just this one. It says not calculated. When I hit run, it'll just run the studies that say not calculated, so it'll run that study for me. Now, alternatively, you can just right-click and say create project. When I do that, it'll say I'm going to set the geometry to this, so that's fine. And then you can see what that configuration looks like here now, and then you can go over here and just hit hit OK to this thing, and then you can just go over here and hit run, and then really interrogate that result more directly. Look at flow trajectories and all that kind of stuff. Okay. Now in the background, it does have full results for all these other things, I believe. So let me so if you did want to interrogate any one of those in between data points, like you just right-click, create projects from these, and you'll be able to kind of play around with them. Okay. So hopefully that answers your question there.
Yeah, somebody had a question on whether the recorded version will be available, and yes, it will. So we'll be sending everyone a link to the recorded version.
All right. I think that's all of them, right?
Yep. Yep. That's the time we have today. I appreciate people joining us. Feel free if you've got any, as you start to work on your models, if you're running any issues with this, call our tech support line, and hopefully we can work the details with your specific models.
All right.
Thank you, and have a good rest of the day. Bye now.
Thank you. Bye-bye.